your EVM compatibility. Um, Given that like moving Ethereum in more of a ZK direction seems to be like a thing right now, I'm not really sure what the Ethereum developers are thinking about this. Um, that would be kind of an interesting open question in my mind. So those are just that's what I could kind of wrap together in just a you know 15-20 minutes of reading. So I'll pass it to Jenna.
I guess I'm weirdly comforted that nobody can just like grok this stuff on the first bounce. Um, so my strategy is I've been trying to figure out how to contribute here instead of just being dead weight, is I've come back to the pattern recognition, maybe many of us have read it. It's the first William Gibson book in the Blue Ant trilogy. And that there's something that the parts of this that I can recognize. So for example, in I think it was in the Notebook LM thing, it I asked, so what does the word precompile itself emphasize? And the answer is, okay, you put the the work ahead of put the work in the right place. And that's a pattern that I think is, for the rest of our lives will always be true. See if you can figure out where is the right place to put the work. And anytime you can find that, whatever you're doing, the whole thing will get a lift. So cool. Another one that came to mind in terms of pattern recognition was attack surface. So anytime you move the work somewhere else, the handoff becomes an attack surface. So at the risk of using a US football, and when you hand the ball off, you totally risk a fumble or a hijack. And so how do you for this process, this precompile stuff, how are they going to have those handoffs be safe? And both from the perspective of just a dumb fumble versus actually getting hijacked in some way. What was the third one? Oh, this is a real theme for me this month, but somewhere in the research in this work that we were reading, they mentioned stochastic versus deterministic. And so yeah, that's right. It's from the screenshot that Anuraj that you dropped, that keeping things deterministic and provable within a blockchain context. That was the quote. Um, it feels like there's just a big theme right there that is worth never forgetting. Deterministic is always going to be the kind of safe guardrails that let you have outcomes that are predictable, while also being golden handcuffs that will screw you up. And because I think Nathan, you mentioned this, is edge cases all the way down that you'll never be able to anticipate the every possible situation that might come up for some rules. So some stochasticity will always be in the mix. I think those were my top level, Oh, I know the last one that's been on my mind a lot is um, how the rest of us can benefit from the galaxy brain people who really are able to think this stuff up and follow it, and that this LM coding that a bunch of the rest of us are doing are letting the rest of us make use of those brains. And so I think there is clearly like some thievery that's gone on because those guys aren't getting compensated. But it is kind of amazing being able to harvest the brains that we're able to create these patterns that underlie all of our modern software. And then Goombas like me can jump in and make use of that stuff. It's just been an interesting 6 months, I would say. So passing up to Ben now.
Yeah, so I mean, obviously, I've known about precompiles for a long time, but this is actually the first time I've actually really interrogated them. Um, and I put a link to the chat, and basically, so I know that precompiles are like sort of special functions built into Ethereum that are vastly cheaper than they would otherwise be if they were written in EVM. So like, basic hash functions precompile. This allows you to, actually do a hash in a meaningful way. so your contract can actually deal with hashes. And I've known that, like, obviously doing this, there's only this limited number of basically precompiles set by the network, and that, adding precompiles is a hard fork. So, there's been politics around that. And I've watched this from a distance, and I actually, interrogate, why is a precompile really so much cheaper than just writing it in EVM? And, well, why can't then I just, publish contracts as precompiles and, have the system be vastly more scalable? Um, and it's funny that, felt like it took Claude by me. I left it on Max by accident, but it took Claude a long time to answer these questions. But basically, it's almost a political thing about, what gets a precompile, because it looks like precompiles are much harder to upkeep, for Ethereum, because they're basically hard coded into the node itself. They're not using the EVM. Or they only expose themselves as the EVM as like a virtual contract, whereas the actual implementation has to be done node side. So, you couldn't actually ship one without, the ability to arbitrarily change node side code for everyone, which would, make it, be bad. Break the virtual machine sort of thing. And so the question of what becomes a precompile, since they're so much more efficient than, what a normal thing is, how do we, everyone wants to be a precompile, obviously. But, at the same time, the node, sort of creators don't want there to be too many precompiles, because, if, these are all implemented in different languages, and if they're ever even slightly off, the network is going to split. So, the question of how do you, what should be a precompile, and it's sort of, it's a funny, it's so, the original EVM was sort of like an abstraction of, what kind of computer can we put on this chain, and, like, let's set up a bunch of a virtual machine with a bunch of opcodes, and it was sort of, I hate to say it, it was made very slapdash. That's why you have like the 256-bit words, which, make a lot of sense from, like, oh yeah, because that means a word can be a hash or an address, and it makes so much sense. But it's like they obviously hadn't looked like, wait, hold on, is that actually remotely efficient when actually simulated on a real 64-bit CPU, or are you just, ballooning the whole computational process of doing all this? Um, and of course, once they made it, it was very hard to change. Um, and so, precompiles are almost like a hack around that. So, like, there's things that Ethereum needs to be able to do cheaply. So we'll just make those into precompiles. And then, all your normal smart contract stuff are, the EVM code, which is much less efficient and more of a pain. But, it's much safer for us to, let you just add that, permissionlessly, because there's no way to, like, whatever, it's in the EVM, so it can't get out of the virtual machine. Whereas these precompiles are much more dangerous objects, much bigger attack surface, much bigger set of things that could go wrong. So it's interesting because, it's just one. They could have made it so, like, maybe, I'd be more actually interested in maybe a version of Ethereum where there's a lot more precompiles, and the precompiles were a lot more like building blocks. So, like, you had more like precompile Lego rather than a full EVM. I'm just spitballing here because I haven't really thought too hard about this till, like, right now. But, um, that way, if you had like a bunch of precompiles that did sort of basic tasks, instead of writing EVM code to do what you wanted, maybe you could, um, Lego these precompiles together, and that might end up being, an order of magnitude more efficient. Of course, doing that would mean much more precompiles, much more powerful precompiles you have to be careful about. Obviously, the Lego analogy is they should be very simple, so you can put them together. Would that actually be more efficient? I don't know if that's ever been explored. So I might just be bullshitting. But that's certainly something that comes to mind. It's just a fascinating. This is like one of those interfaces that, it's almost a leaky abstraction, where you have this sort of, the perfection of the EVM, compared to like, you know, the reality of how CPUs actually crunch through numbers. And, you know, things can run in perfect EVM heaven, but, you know, if you want to actually get some serious efficiency on some relatively computationally hard tasks like hashing or signature verification, you gotta break that a bit just enough so you can actually get, you know, these powerful things in there. Um, yeah, so I think I will pass it up.
Yeah, reading about, so I basically had read a little bit about it when I was trying to read about the KZG commitment. I think there is a precompile regarding that which generates the KZG proofs in the EVM itself. So I have read a little bit about it, but like what I found interesting was like I have done uh, a similar kind of stuff in like real hardware. So let's say if a microcontroller doesn't have a floating point unit, what you do is basically you pre-calculate the function values. Let's say you want sinusoidal wave functions, which you know you are going to use. So what you do is like you calculate the values and store it in memory, and then you just kind of instead of computing it on the fly, you just take those values from memory already wherever it is stored. And and in like if you are doing like a system on chip, you could do a lot of the calculation in hardware itself, but the main question becomes like which part of the entire computation you put it in actual hardware, because that increases the cost. So I think kind of it becomes like a human problem. Like some people want their computation to be in hardware, and because like it and the software can be changed later on, so then it becomes like a people issue, like who which part of the compute stack actually becomes hardware. So that is what like I found a little bit interesting. uh, and what else I was thinking about? uh, yeah, like, and the other thing was like how it kind of it enables a different uh, let's say L2s or other compute stuff to exist without actually like being on the chain itself. So that's how I went to the co-processor chat paths. So you could have like lots of other kinds of processing going on, then you could just submit a small proof to the main chain, and then the question becomes like what needs to be on the blockchain, and like what needs to be what if there needs to be a consensus about that compute or not. So that becomes a question. Um, yeah, so those were some thoughts, and then passing on to Venkat.
All right. Yeah, my immediate first thought on reading about this is it reminded me of the old RISC versus CISC debates, right? Keep the instruction set small and minimal and extremely, atomic instructions versus support lots of complex instructions. So I started chatting with ChatGPT about that, and it agreed that there was some similarity there, right? Like precompiles generally pop up as a solution when you're trying to provide more complex functionality, like cryptographic primitives or math code processors and things like that. So there's a trade-off between uh, being able to express and do both in the full range of simple to complex operations at the same low level of abstraction, and the fact that complex operations actually do take more resources. So putting them at the lowest level of abstraction usually means you're sacrificing performance, right? So if you try to do everything with EVM bytecode or CPU integer operations, things will be incredibly slow. That's why you have accelerators of various sorts. So it's a recurring problem that's not specific to blockchains or even chip architectures. And ChatGPT actually suggested the better analogy was not RISC versus CISC, but the division between what the chip does at the ISA level on the hardware, so ISA is instruction set architecture, versus what the operating system does on top of it, right? Um, and I was asking, like, is there like a fundamental problem here that you never really know anyway who is actually how your um, computation request is actually being handled, right? So it may be specified at the lowest possible level. So it might be a hardware level opcode, or a virtual machine level opcode, or whatever, and you issue that instruction. But because you're not actually able to audit or verify the full stack of where that thing actually goes and is executed, there's lots of basically middleman characters along the way. You actually don't know, like Windows or Mac PC. You think, like, even if you're like a systems programmer, you think you're trying to get a particular opcode executed, but there's many layers in between that can intercept and do something else with it, right? So the point is, this is not specific to whether or not a particular opcode can or is supported. It's actually a question of whether you trust every layer between you and the target layer, whether it's actually going to pass it through or decide to do something else, right? So even a very simple operation like, add two registers, you're talking to the operating system API, which is then talking to low-level kernels, which is then talking, I don't know, there's probably 6 other layers in there. And at any one of those places, you're trusting that each one is actually going to like pass through to the advertised target layer, right? So, for example, forget blockchains. Take like the x86 architecture. If something claims to be x86 compatible at like a application level, and you are trying to run x86 code on it, you actually don't know who's actually running the code at what level, right? And I was chatting about this with ChatGPT, and it's like, apparently this is not just like a thing you can design and architect your way around. It's fundamental to computer science and the basics of universal Turing machines, that there's literally no way to tell. Like, perfect emulation is possible, except for a few very subtle heat signatures like execution time. So in principle, you can create like abstraction layer that you cannot tell is not sitting above another layer, except for things like, it takes slightly more time to execute or something. Uh, so there's a fundamental problem. And apparently, Ken Thompson, in his Turing Award lecture, I've read several of them, but at some point I feel like maybe we should make this a track. We should just go through and read all the Turing Award lectures. But his famous talk was apparently this paper called On Trusting Trust or something, where it points out that, yeah, you can hack compilers and things like that because there's all these layers, each of which is in principle like perfectible, except for like subtle signs like timing, which are really hard to detect, by the way. Um, which means that any claims of things being decentralized and stuff, it's, I don't know, interceptable. Um, okay, but the interest is, I was probing further about what is actually then the interesting difference between the claims of decentralized trust and so forth versus, just trusting Intel or ARM for their ISA. So here it gets interesting. The thing about the EVM, unlike even the JVM, so Java Virtual Machine, is there is no actual, you know, uh, standard target hardware, so to speak. So what you actually have is the consensus overlap of all the clients, right? So Get and Besu and all the others. At some level, there is no such thing as a reference machine running the reference EVM. What you have is the intersection of actual clients who do consensus mutually replaceable or interchangeable behaviors for particular opcodes. That makes sense, right? Whereas for something like, say, Intel backing the x86 architecture, there is kind of like a source of truth, which is Intel and the way Intel chooses to implement it on Intel hardware. So there's at least some notion of like authoritative truth backed by one entity. It can be autocratic, and the autocrat can lie. Intel can like make claims that its hardware doesn't actually fulfill. But the point is, truth converges on one node. Whereas in something like the EVM, and this is true of other like centralized computing virtual machines as well. Like, the Java virtual machine is a spec that was started by Sun, and I think is now maybe a web standard or something, but it's still kind of like centralized. But the EVM is, it's kind of like a hallucinated machine that doesn't exist. So the idea of like the EVM, yes, it's an abstraction layer above hardware, but it's even stronger than that. It's an abstraction layer above hardware that exists only as a function of the consensus, as the behavioral consensus between the various clients. So all the clients say that this particular subset of the opcode space, we will all agree to implement in good faith in kind of like similar ways, and you just have to trust that we are all doing the same thing that are kind of comparable, right? And yes, there are some protections. Like you could have full source for every client and then audit that code, and presumably there's ways you can like um, sign the build process, and so you can verify that the build came from the verified source or something like that. But I suspect even there you're ultimately ending up trusting somebody. So but the point, why can you trust the EVM more than you can trust, say, the Intel stack or the ARM stack? And ChatGPT made the claim, and we should think about it, that the Ethereum EVM is something like common law. So it has the robustness of emerging from the consensus of multiple client behaviors, as opposed to emerging from the claims of a single vendor like Intel or Sun or ARM. So I'll have to think about this. But if so, then yeah, there is a case to be made that a decentralized blockchain-based EVM does offer some trust guarantees that are, in a social sense, stronger than what a private corporation can offer, or even Linux. I would say the Linux kernel, even though it's not a private corporation, it kind of is run like a corporate group, right? Linus and the core committers and stuff. So in principle, they could collude or something. Yeah, so that's kind of my initial set of thoughts here. But this requires more thinking, and maybe next week we'll read the Ken Thompson paper and try to understand the fundamentals here. Back to Anuraj.
Yeah, one thought about the social consensus part of the EVM is that like the upgrades become really difficult, right? Now there is a talk of about upgrading it to REST 5. So basically the social part is, I think, more difficult than the actual technical part. Any more thoughts? If not, then we meet in 2 weeks. Thank you.
Anuraj, are you going to do the act talk? Just checking before we bounce.
Yeah.
Okay.